Hello. There's an anecdote that goes around MIT involving computers and magic. In the early days of mainframe computing, one of the researchers was working on one of the computers, found a switch on a side panel. And that switch had two positions, magic and more magic, and was set on more magic. So out of curious academic interest, that researcher switched it to magic, and the computer crashed immediately. He asked a couple of other colleagues what could be going on, so they opened the panel, and there were two wires. One wire was going inside the computer, the other one was inexplicably left open. So if you know anything about electrical engineering, that doesn't make sense. It's not explainable. But what they did is just gave up. They agreed that the computer was running on more magic rather than regular magic, and they moved on. What I'm going to talk about this morning is about how we came to frame the computing machine, the latest miracle in human history, in terms of human words, and how, through doing that, we allowed numerical systems to make unequivocal decisions about our lives. The original scripture for the computing miracle can be traced back to the Turing paper, which, as most papers, only bothered itself with ideals. It offered a theoretical solution to a theoretical problem, and the description of vague guidelines for the physical implementation of the machine was just an afterthought. What Turing had in mind was the possible elaboration of a solution to the Einstein-Dunks problem. And the Einstein-Dunks problem, it's basically just the decision problem. Can we make an unequivocal, an unambivalent, a binary decision about a given problem? Turing seems to think that we, as humans, cannot, because we forget things. So if you can devise a system to circumvent these human limitations, you could know all there is to know, and in Turing's case, all there is to know about computable numbers. That paper, then, is just the newest iteration in our long list of claims for universality. It was written in English, but it was about numbers. The purpose wasn't to have a physical proof of universal decision-making. The purpose was mental reassurance. It was to know that it was possible to know. Because if we as humans weren't able to hold and manifest that knowledge, we could rely on the fact that there was a system that could, something better than humans at storing and processing information. Belief systems have always relied on names, and as scientists were following Turing's word and bringing that machine into our world, they described the range of binary operations with the very poetic name of truth tables. A truth table is obtained by cross-referencing truth functions with binary input. At the same time, a shorthand, but with long-reaching consequences, came with the correlation of Boolean logic. And Boolean logic says that the equality or the inequality of a given mathematical operation, of a given ideological wording of a relationship, could be assessed only as true or false. So that system of binary encoding took a life of its own and became slowly a Manichaean system. The Turing machine in itself was only the consecration of thought into matter, of rational thought, science, into rational matter, machine. And that consecration had believers from the very start because they had a computer at MIT, and that computer was running on magic. It was unquestioned by those few clergymen as they scattered around universities in the United States, because they knew that to know how to work the machine is to have, at one's hand, the ability to decide for certain. It's the ability to find an answer and truth as the output of successive steps of read, process, and write. But in order to have the computer provide us with those answers, we had to set standards. So it was decided that the variations in electrical current would be represented only as 0 or 1, a binary digit, so that's a bit. So plus the mathematical operand, which adds two whole numbers, had a binary representation. And that binary representation became 111001111101011000010. But binary was far from making programmers' lives easier. And we started looking at better and better ways to talk to the machine and ways to overcome the problem of physical systems, which is they don't understand what we say. The research assistants started working away from machine code, which was the faithful mirror of electrical circuits. And they worked on something called compilers for a language called assembly. And a compiler is something of a translator, if you will. It takes a language, translates it into another language, and so on until it reaches the desired state of electricity. Because if we were to solve our problems, if we were to ask the machine for what decisions to make, we had to renegotiate the terms of understanding, and those terms had to be in English. The first step in that process was to agree that the word add, A-D-D, would become an abstraction of numbers. It was agreed that this word, this idea, this relation, could be linked to a set of binary numbers, just zeros and one. And so add became
11101111010101010.
That's how we moved from thought to numbers and then to words. But still, those words were highly specific. One typo and the computer would throw an exception, ignoring the fact that the English language is full of exceptions. So up to that point, the languages that we designed to communicate with the computer followed a very strict paradigm, which we call the procedural programming paradigm. You take an input, you process it, you have an output in a very linear fashion. And reading and writing in the style of procedural paradigm is based on certain words, which we call data types. A data type is a type of data that the computer sort of understands in most architectures. You can have, for example, an integer, which is a whole number, and you can add it to another whole number, and the computer decides on the sum of these two whole numbers. You can have a string, which is a word. You can look for characters inside that string and look for another word. And so you can ask the computer if the word life contains the word if, and the computer will decide that such a statement is true. So for me, the second moment in the computing miracle was the shift between procedural programming and object-oriented programming, in which we replaced these data types with data structures. This is when computer science became computer fiction. Because object-oriented programming allows us to write instructions which relate to our world. It allows us to use these primary data types in order to create our own. So 2 integers together become a 2-dimensional vector. 3 integers together in the range of 0 to 255 become a color. A mix of strings and integers can represent a user profile in a corporate database. This allowed us to recombine the building blocks of the Turing paper. It allowed to create, describe, and act upon clusters of data. And naming the data, those chunks of digital clay that were to form the golem of our world, came just for a simple endeavor of relieving programmers from the mental somersault of having to describe everything that was around them. So that act of naming resulted in a manipulable, processable representation of our world. From making decisions with and about numbers, we ended up making decisions with words as numbers about our physical, non-discrete environment. A machine doesn't define red as being the color of blood. It defines red as being a value of 255,00 passed from the central processing unit to the graphical display device at one given pixel coordinate. But then we can place that value within a greater data structure. We can name it red. We can tag it with blood, love, happiness, danger, and all weight those against each other. So this is how we made the machine, if not understand, at least seem relevant to the mental representation of the world that the programmers lived in. If we could reorganize a word into bits, and bits into bytes, and if those bytes could mean anything, then it follows from the Cartesian method that we can abstract anything. As Georg Nis tells it during the first exhibition of computer art, you can make a computer paint like an artist. The only thing you have to do is to explain to the computer how to paint like an artist. So this is how we started explaining all the things that we needed, from mathematical operands to letters, to words, to colors, to brushstrokes, and then finally to humans. The miraculous promise of solving the decision problem was too beautiful not to try to fulfill. At this point, everything we can think of, everything we can effectively represent in semantic terms became computable. We could give the computer instructions such as the best way to do this or that, provide that this or that, make sure that it was computable, and then ask the computer for a solution. We can represent a problem, ask it for a solution, and modify the instructions until we find a solution that fits a worldview, fits the worldview of the person who wrote the program, or fits the worldview of the person who paid the person who wrote the program. In 1970, John Conway came up with the game of life, in which zeros and ones were performing as life and death. The arbitrary number of neighbors were the sole arbiters in the existence of each of these cells. And that toy, that mathematical toy, which decided on its own, better and faster than any of us, who would live and who would die, that toy was taken seriously by those who did not know or by those who replaced knowledge with belief. So at this point, input, process, and output isn't anymore about whole numbers. It's about our life expectancies, our career paths, our happiness levels, our language literacies and voting intentions, all represented on a scale. And because you can normalize the scale, because you can represent it between 0 and 1, you can decide upon that scale. Conway's game of life paved the way for other games of life, less mathematical, but more deadly. Tenure tracks are justified by articles published for the computing models of civil violence. Promoters and urban planners are playing around with simulations to fix low-income housing. Private companies are writing instructions for the computer, a decision-making machine, to inform a judge, a decision-making human, whether another human, described through a limited set of words, entered in arbitrary databases, transformed into code, and set into dualistic electrical signals, whether that human is more likely to commit a crime again in the future. The computer decided some humans were more dangerous than others, and we correlated these humans as low-income citizens of color, because it was describing the world in the words of those who had made it. Around the same time, in 1966, ELIZA was born. Its creator, Joseph Weizenbaum, was also a professor at MIT, and he expressed interest in modeling human conversation. So he had a program which was a set of instructions as a back and forth between machine language and human language, representing decisions made by carefully crafted processes, outputting very, very vaguely worded sentences. On completion, he referred to it as a parody, but he still gave it a name. Weizenbaum's assistant, however, referred to it as an interlocutor and called it by her name, ELIZA, because it was something to talk to, for lack of a better someone. And these instructions, as become really, really quickly clear, don't add up. They don't make sense. It's really easy to see the machine, but for some reason, we choose to see it as more than the sum of its parts. We choose to reflect only in what we are presented with, in the computed output that has been curated for our expectations as a polished mirror for optimized user experience. Because if we give it a name, then it's alive. So now is what happens when we translate our limited expression of all which surrounds us into the subjective objectivity of our mechanical decision maker. What happens is what happened with all other miracles. They invalidate the possibility of anything else. Whatever happens, might have happened, or might happen, is explainable by the computer. Its supremacy happens through the doesn't happen through the automated calculation of numbers. It happened through the automated calculations of love, hope, health, and happiness. The supremacy of the computer happens in our unwillingness to understand how it works. It happens when we abandon our own human complexity down to the very theoretical models of our brains and behaviors and force that complexity into the machine's comfort zone. So that retort of quantizing the world, then, is just a matter of recognizing how absurd such an endeavor is and acknowledging that our modern miracle, our modern magic, is only made of numbers. Because Turing machines, in the end, are just nothing more than a very elaborate assortment of rare earth minerals put together in the People's Republic of China and assembled by underpaid and suicidal laborers. As there was no magic in the authority of the Catholic Church, and there was no magic in the neoliberal free market, there is no magic in the computer. But this does not prevent us from being excessively attached to those belief systems. And our emotional binding to numbers is precisely what prevents us from moving past a paradigm of accumulation, no matter how unsustainable it is. So framing it as a lack of understanding is still blaming the system for being too complicated. I don't see it as a lack of understanding. I see it as a lack of effort. The word of the Catholic Church was written by men who set up that system to serve the vision and impose it upon the world, benefiting from the fact that their believers were literally illiterate. They set up beautiful pieces of colored glass to convey their message, and the only thing we got better at today is that now our colored glass responds to touch. Every single piece of software today is still written by men. And those men seem to aim towards godlike omnipotence, an ambition that's unchecked by the rest of us. Specifically, those words are written by a very limited and yet potent set of our world's population. Those writers are mainly the male engineers working in the Bay Area who know what they're doing, if not why. So to conclude, let's just remember that computers were built by humans, and there is no reason why other humans could not understand what they do, how they do it, and why they do it. This is even more necessary as those machines are ever expanding their range of operations. When you think about it, Gutenberg invented the printed press to spread the word of the church, and Luther seized it to question it. Turing invented the computer, and it is up to us to take a close look at it and see how we turn it into an unquestionable means of understanding, explaining, and deciding. Because if we were to allow for the continued existence of other miracles in life, then perhaps we should start by understanding how we came to objectify that life.
Thank you.